Hello, everyone. Welcome to my keynote on the opportunities and challenges in machine learning. Machine learning, we all know, is widely considered as the motor of modernization. It is driving innovation, economic growth, and the progress of civilization. There are several areas in machine learning that provide ample opportunity for innovation. Given that artificial neural networks are universal function approximators, the possibilities of deep learning frameworks that build upon artificial neural networks are immense. One such framework, called generative adversarial network, has given rise to several profound applications in a relatively short period of time. There is now a zoo of different types of generative adversarial networks used for various impactful applications. So we'll look at GANs in this talk. GANs are generative adversarial networks. Elucidate some of the recent work that uses GANs and examine the potential of GANs. We'll also explore some application domains such as education, social innovation, and software engineering, which present substantial number of opportunities and challenges for the application of machine learning. So before we get started, I need to introduce some guests. Does anyone know who this person is? How about this person? They are all fictitious characters generated by a GAN. So in fact, there's a website called thispersondoesnotexist.com from where I got these pictures. So they're all fictitious images. The persons don't even exist. How do we generate these pictures? It is by playing a guessing game. So it is similar to a game called Akinator, or sometimes it's called Bullseye, and other times it's called 20 questions. So the game basically is that one player has to guess a person or think of a person in his mind, his or her mind, and the other player, if you're playing with a computer, it is the Akinator. So the computer or the second player is going to guess who is in the mind of the first player by asking a few questions to which the first player needs to answer in yes or no. So after a few questions, the Akinator or the second player is able to guess. For instance, the first player might have thought about somebody, and the Akinator or the second player is going to ask, is the person a male or a female? Then the first player is going to say male. The second player is going to ask, is the person a politician? And the first player might say yes. And things like that. So in a few questions, the Akinator or the second player is able to guess the first person's, whoever is on the first person's mind. So in a similar fashion, there are two players in this generative adversarial network framework of deep learning. So the first player is called the generator, and the second player is called the discriminator. So another analogy is that of a small child, an infant, or a kid who is learning to write the alphabet, letters of the alphabet. I still remember the days when my mom taught how to write the letter A. So she would give me a pen and paper. The first attempt, I would just come up with a scribble something like a scratch here. Then my mom would say, no, that's not the way to write A. And she would give me some feedback, some amount of feedback. I still remember the feedback she gave me. She said, you have to write two circles, one full circle and the other is a half circle, and join them together. So that's a small letter A. So using that feedback, I would improve slightly, but my mom would still say, no, that's not correct. You still have to improve and give some more feedback. So after many attempts like that, I eventually learned to write the letter A. So in a similar fashion, the generator first generates some random noise, a scratch, to generate the image in the efforts to generate an image. The discriminator, who acts like an adversary, says, no, that's not the way, and provides some feedback in the form of a loss. So using that loss, the generator improves slightly. And after many attempts, eventually, the generator is able to produce a real looking image. Then the discriminator is fooled and says, yes, that's the image of a real person. So that's the framework of GAN. The way, a little more detail into how it works. So we all know the parent is already trained, so can tell if the written letter is correct or not, and provide some feedback. So similarly, the discriminator is already trained first, so that it can tell whether the image is that of a real person or not. And if it is not a real person, then feedback is passed to the generator through a loss function. So this is the beauty of deep learning. You don't need to extract the features of the data to understand it. It is just a bunch of numbers, in this case, pixel values. So, so first, the discriminator learns to recognize images by getting trained on a bunch of real images and fake images. So again, it's an iterative process, primarily guided by the loss function, which is like a loss, typical loss in sales. It is similar, but only thing is simpler losses will not help learn faster. So the loss is not just the difference, but slightly more sophisticated to make the discriminator learn faster. So based on the loss computed at each iteration, the discriminator eventually learns to adjust the importance given to the pixel value, pixels in the image. So each pixel has an weight, an importance that is adjusted by the discriminator based on the loss function computed at each iteration. So you can think of loss as a lesson, a learning. As the saying goes, no gains without pains. Same in machine learning. The loss provides the lesson, the pain that the discriminator needs to go through and adjust its weights for the pixels or whatever features are computed in the image. So once the discriminator is trained to recognize real and fake images, the next turn is that of generator. So generator similarly gets trained. So initially, the generator produces random noise. It takes a random variable and produces Gaussian noise typically. As in, it takes Gaussian noise as input and then produces some not so relevant picture. And then the discriminator helps the generator to learn to generate good images, good quality images. So this is a summary of how it goes. So typically the features are extracted using a framework called CNN, features of an image. And then the discriminator and the generator both learn to work together and generate a real looking image. So this is an illustration of generating handwritten digits. So you can see how it is all noise in the beginning and improves after many trials. So as the Nobel laureate Richard Feynman said, "What I cannot create, I do not understand." This quotation is very much applicable to big data and using generative models. So what we saw was basically a generative model. To understand data, we need to create data. Until we create data, we haven't understood data. So the first opportunity we are going to talk about is the framework called generative adversarial networks. So there's actually a whole zoo of generative adversarial networks. In fact, if you search for generative in Google Scholar, it returns more than 78,000 papers. If you search for generative adversarial networks. So there's actually, you can take a look at the website as well. It's on GitHub, and you can see how the number of papers is growing exponentially. And these are all the different GAN frameworks used for doing various things. So we used one such framework, GAN framework, called the CycleGAN for some of our research. The original CycleGAN was used to convert between similar looking images. For instance, in this case, horses to zebras. For that kind of a problem, we have had we would have needed several paired examples in the training data set to train a machine learning model. But getting that kind of data may not always be possible. So it is not possible to get the exact a horse's image and an exact copy of a zebra image, right? It's hard task. So that's where CycleGANs help. CycleGAN learns the mapping between an input image and an output image without needing any paired training examples. Instead, they use what are called as cycle-consistent adversarial networks. So, so we use that framework, CycleGAN, to convert melodic frameworks called in India, it's called raga. So we used CycleGAN to convert raga in the style of North Indian music called Hindustani to a raga in South Indian music called Carnatic and vice versa. So the way it works is CycleGAN has a pair of generator and discriminators. So there's a pair. There are two generators and two discriminators. Here we see the first pair in pink and the second generator discriminator pair in green. The first pair works to convert the music in a North Indian raga called Bhairavi to a South Indian raga called Shanmukapriya, and the second pair does vice versa. The generator discriminator pair works just like before, except that instead of random noise to start with, we input original music notes in Rag Bhairavi. The original samples are shown in yellow. So these are the original samples. Simple adversarial loss is not enough, so we compute cycle consistency loss to determine how different the generated raga is from the original sample. The cycle is shown in the arrows. The thick arrows denote the transfer from Bhairavi to Shanmukapriya, and the regular arrows denote the transfer from Shanmukapriya to Bhairavi. So GANs bring together two powerful paradigms: the deep generative models and adversarial learning. So we are planning to use CycleGANs for many such applications. So here's an example of music composed by artificial intelligence. So there is a website called AIVA, AIVA, Artificial Intelligence Virtual Assistant. So that is what has composed this soundtrack. So there's a website called aiva.ai. You can actually sign up there. So the artificial intelligence is basically creating these melodious tunes or soundtracks all automatically. So the next opportunity is music learning, machine learning for music. So one ambitious goal that we tried to work on is to build an automated tutor for classical music. We all know classical music is difficult to master, particularly the Indian classical music requires several years of rigorous practice under the tutelage of a master to actually start uh, singing or singing classical music. So it's an expensive process, and particularly for people who do not have access to the masters are kind of constrained. So if we have an automated tutor which can emulate the function of a master, a music master, then things become much more easier for learning classical music. So we used LSTM, a framework called LSTM, it's a deep learning framework to model the dependencies in the music signals to try to build a music tutor. This is an open access paper, so you can all take a look at it by going to the Elsevier website. You can also watch the presentation that I made on this topic on IEEE.tv. Just go to IEEE.tv and search for my name. You will find a bunch of videos where you can watch this. The next opportunity is using machine learning for education. So there's a lot that can be done here. The first thing is identifying analogies to enhance learning comprehension. Analogies are important in trying to understand a new concept. So we actually gave identifying analogies automatically a try using NLP techniques. Initial results were not very encouraging, but we want to continue pursuing that idea. So that is one area which has plenty of potential. The second area is question answering. So many years ago, for my undergraduate senior project, I used artificial intelligence to build a question paper setting system using Prolog. It was an expert system, one of the 5 primary areas of artificial intelligence research during those days. I'm planning to do the same now, but this time using deep learning and natural language processing techniques. Stanford is already leading research in this area. They came up with what is called a SQUAD, which is a data set for the purpose of evaluating question answering systems. NeurIPS, one of the noted or probably the best, most popular conference for machine learning, hosts a competition in this area. The next idea for education is to improve comprehension using images. So basically the idea is to summarize text using images. So this is a very rapidly growing area. In fact, you would have all heard about DAL-E, which is able to produce images for any kind of idea we have in mind. And recently I read a publication, it's a preprint, which attempts to summarize longer texts like stories. So DALL-E was limited to the length of the text from which the images could be generated, but recently there has been work to summarize stories with images. So that's there's a lot of potential here as well. So these are a couple of pointers for those who are interested in building a question and answer systems. The first is the Google AI's benchmark. This is a set of real questions that users asked when they use Google to search the internet. Google is anyway increasingly being used for question answering thanks to an NLP pre-trained model that they invented called BERT. Again, NLP is drastically evolving as well. So BERT was one of the protagonist frameworks in this area. BERT allows us to use transfer learning for NLP, just like we used ImageNet for computer vision. So transfer learning is a very disruptive concept in machine learning, where you can transfer the learning from previous models to train newer models. So this is the Stanford question answering data set that I talked earlier. So Pranav Rajpurkar and others came up with this data set, and there's a leaderboard, as you can see here. So you can use this data set and evaluate your models. So a whole lot of stuff that can be done using machine learning for education. You can have tutors. You can build graders, automated graders. Then question setting is one area. Predicting performance of at-risk students. Suggestions to improve teaching. We are working on accent issues using deep learning. And so also making education more fun. So gaming-based learning is also quite possible with machine learning. And then personalization. Machine learning has personalized a lot of things, and it can do the same for education as well. So the idea is basically to apply what we learn. I mean, education is not complete until we contribute to the knowledge pool that we learn from, right? So applying machine learning to learning, human learning, is a very important thing to complete the cycle. There's a lot more to be done, and this is a really a growth area that one can focus on. So the next opportunity is using machine learning for software engineering. So today, machine learning is able to predict the next word when we start typing a message in a natural language. We should be able to do the same with programming languages as well, and it is to some extent already possible. So one idea in that direction is also to translate programs in one language to the other. Facebook already has a solution, but it works only to some extent and to only certain languages. They use self-supervised learning to accomplish this task. We built upon that work and tried generating R code from Python. But we were hit with some limitations, which I'm going to talk towards the end. But the paper has been published pretty recently in a Springer journal called SN Computer Science. So you can, that also is available on the online, so you can take a look. So this graphic shows how keywords with similar functions are grouped together, just like clustering. It's all unsupervised or self-supervised. Keywords from different programming languages used in similar contexts are close to each other in the embedding space. So this is the embedding space, and you can see that the keywords used in similar contexts are close to each other. Example is catch and accept. So this is the idea behind conversions between programming languages or transcoding. So the transcoder that Facebook designed uses the three paradigms shown on this slide for doing self-supervised machine translation. Just like we learn better by solving a number of fill-in-the-blanks questions, confusing multiple choice questions, etc. The first two principles of machine translation learn better by mask language modeling and denoising autoencoding. The first two techniques are good enough to translate. The third technique is needed to further improve the accuracy. The next opportunity is for social innovation. Economy grows as more and more people join its core echelons. People are always the most important economic resources. We all know this. So using machine learning for bringing the people into core echelons is an important social target. In fact, there is an ambitious plan, a roadmap for development in Africa for using artificial intelligence for various things like eradicating poverty, improving climate, taking care of the life below water, so on and so forth. So it's an emerging area, and so the first area we are going to look at in social innovation is for using machine learning for energy. So machine learning can help wherever there's a need for predictions to be made. So the predictions in solar or wind energy are useful. First thing is to reduce reliance on not so renewable energy plants. For instance, diesel generators, wood burning stoves, which are prevalent in developing countries, can be phased out and replaced with solar and wind energy sources. So the former, the diesel generators and wood burning stoves, have a high carbon footprint. So we want to replace them with solar and wind energy. And machine learning can help make the predictions with respect to solar and wind energies. And machine learning can also help in lowering losses by proactively suggesting maintenance for the electricity grids. In case there is an upgrade that is needed, machine learning can detect the need for an upgrade and predict the same. And machine learning can also be used to improve battery storage technologies, such as for lithium-ion batteries. So machine learning is like a hammer, and wherever there's a need for prediction, that's the nail that the hammer can hit. So this table lists a few machine learning models used in literature for renewable energy applications. So as you can see, a number of predictions are possible using machine learning. for various forecasting needs like wind speed, wind energy, solar irradiance, and so on and so forth. Irradiance is basically the energy, the radiant energy emitted. So this is the application of machine learning for transportation sector. So machine learning can be used for predicting the bike availability. We all know rented bikes in US and some other countries. You can rent a bike and a bicycle basically and leave it at your destination. So this will cause an imbalance because some destinations are more popular than the others. So bikes will get accumulated in one location or a few locations more than the other locations. So to avoid this, by making predictions of the bike availability, the prices can be adjusted so that the bike availability also proportionately changes. So machine learning can help in bike rebalancing. And a whole gamut of applications are in the V2X or vehicle to everything paradigm, where machine learning can be used. So electric vehicle batteries are probably the most cost-efficient form of energy storage. So they can be used, and the other thing is it's energy on wheels. So it's a very powerful paradigm. You can actually store electricity in the batteries of electric vehicles and push them to the grid if required, and to homes. So that's there's plenty of potential there, and machine learning can help make the predictions there also. Similarly, for waste management, there's a lot of work that has happened. We all know when hazardous waste is misclassified as a non-hazardous waste or treated as non-hazardous waste, the government, the regulators can impose hefty fines. In US, it could be as high as several thousands of dollars a day. So machine learning can help classify the waste as hazardous or non-hazardous. There are a lot of, and it can also help estimate the waste generation so that things can be planned. So this is a summary of that work. And then ecological footprint prediction itself can be done using machine learning. And the byproduct is that you can determine the key contributors to the ecological footprint. As you can see, one of the key contributors that the machine learning models have identified is the industrialization and urbanization. Most of the contributors here listed here are basically related to urbanization. So this can be determined by machine learning. So these are taken from my chapter, my book actually. The first chapter talks about machine learning for ecological sustainability. So the previous few slides that you saw were from this chapter, and if you want more details, you can refer to this. Now, coming to the challenges, first challenge is the computing resources. Like I mentioned to you, when converting the language from R to Python and vice versa, we were limited by the resources that were available to us, the GPUs that were available to us. So this is a nice paper illustrating the kind of energy and memory requirements for deep learning models. So these are popular image processing frameworks, and you can see how the energy costs really shoot up. Similarly, the memory costs, memory requirements. The next challenge is the quality and quantity of data. So if you look at this slide, this from a paper, the left image shows some graffiti on a stop sign. But human beings can still recognize the stop sign without any problems, and they can bring the car to a halt. But researchers tricked the deep learning system, the image recognition classifier, by putting these boxes, black and white boxes on the stop sign. And the deep learning model was tricked to recognize this right side stop sign as a speed limit 45 sign. So this first is looking like a 4 and the other is looking like a 5, whatever. And the deep learning model got fooled to recognize this as a speed limit sign instead of a stop sign. That could be disastrous. If such things happen in self-driving cars, it could be disastrous. So quality is an important challenge to meet. And this is from another paper. Here, the researchers added a very small amount of noise, which is almost imperceptible. And the deep learning model was tricked into believing that the image is that of a gibbon. So in the first case, the deep learning model correctly identified this image as a panda, but adding a very small noise to the image, which is not even perceptible to the human eye, the deep learning model believed that it's an image of a gibbon. So that's also a problem. And then veracity of big data is a very big problem, we all know. So the problem is not just with data that is media like images and videos, but the problem is in fact more complex when it comes to simple data like feeds. So some of the ideas of addressing the veracity of big data are in this book, which I wrote a few years back. So fake news is a really big problem, which is still not solved. For more details, you can look at this book or again refer to the video on IEEE.tv, where I addressed veracity of big data. Now, coming to the quantity, a professional acquaintance working in the area told me that they need billions of miles of driving data for self-driving cars to be production ready. So getting that kind of data is a huge challenge, not just for self-driving cars, but for even simple applications like the application that I mentioned of transcoding from R to Python required quite a lot of data. And still the results were limited because of the lack of data. So with all these applications, I'm sure you are convinced that machine learning is the motor of modernization. Machine learning will continue to be a key economic driver, and it is exciting time to be working in this area. I thank the organizers for giving me this opportunity. Professor Vishal Kumar, thank you. And thank you all for listening patiently. And you can always contact me with questions. I'm searchable on the internet. You can send me an email or message me on social media, and we can take it from there. I know I'm not able to join live, but hopefully this presentation would have helped. And any questions, please feel free to reach out to me. Thank you.